Eric Archer here from TI, and today we're going to look at ocean currents. Have you ever been swimming in a body of water that has sort of a push or pull to it? You can feel yourself moving through the water. Well, that's a current, and a water current can supply a very strong force that moves water and objects through the water through a great distance. You're probably most familiar with water currents in relatively shallow bodies of water, such as streams or rivers, or maybe you've been to the beach and you're out in the water and you feel that sort of push or pull. However, did you know that there are also water currents deep below the ocean surface? And that's what we're going to explore today. What causes those currents? What causes that water to move so far below the surface? Before we get started, I'll remind you that you can follow along using this lesson and do the simulations yourself if you'd like. If you go to www.TI-Nspire.com, and the lesson we're working on today is called Ocean Currents. It can be found under Earth Science. And to use the lesson, you need to download our software, which can be found at www.education.ti.com. And that way you can interact with the lesson on your own. If you're unable to do that, that's fine. You can absolutely follow along in the video, and I'm going to work the simulations for you, ask you questions, and we'll go through the answers to those questions. Okay? With that, let's go ahead and get started. Okay, so I've got my file Ocean Currents from ScienceInspire.com opened up in the TI-Nspire CX Premium software. I'm on page 1.1, and you can use this file on either the software or you can use it on a TI-Nspire CX or CX2. It'll work with either of those. All right, let's go to the next page, 1.2. Here's some background information that's very interesting. So ocean water it's moving constantly through the global system of deep ocean currents known as the oceanic conveyor belt. So that's sort of the key point to this whole activity. What is this oceanic conveyor belt, and how does it work? I mean, why is there water movement below the surface of the water? So the deep ocean currents are not the same as surface or wind-driven currents, and these are what you're probably most familiar with. So, I mean, you see this. You'll see, maybe you've seen a movie of like a person on a surfboard with like a big sail attached to it. They're windsurfing because there's so much wind at the beaches that they can catch a ride essentially on the water with the wind pushing them. Other folks, on the water, a captain of a ship or somebody just out with a kayak, they have to be aware of which direction the wind-driven currents are pushing or pulling them. So it's a constant sort of thing that happens. There's always a current on the surface, and they're typically stronger than the deep ocean currents. And that's that next sentence is here. So deep ocean currents move at much slower speeds, a few centimeters per second, whereas surface currents can move anywhere from like tens to hundreds of centimeters per second. So big difference. Now the force behind surface currents is typically wind. That's why we call them wind-driven currents. But what's driving the deep ocean currents? And that's what we're going to explore and look at here in this activity. So it's estimated that it could take about 1,000 years for a cubic meter of water to travel through the entire system. And we've got there's a nice simulation that's going to show you a little bit about that here in a few minutes. All right, page 1.3. So in this activity, we're gonna look at the oceanic conveyor belt and try to figure out what environmental factors are driving the movement of water and the deep portion of the ocean. And we're gonna look at some different parameters that maybe could be involved. Maybe they're not. We'll have to experiment and see. But we're gonna look at wind, which would be obviously on the surface, pH. Temperature, and pH is how acidic or how basic something is. So when you hear like vinegar, which is a sort of an acidic food product, or bleach, which is more of a basic cleaning product, that's what we're talking about. We're looking at the pH of in this case, ocean water. Temperature, we're going to look at temperature differences to see if that has an effect. And then salinity, which is how much salt is in a particular volume. in this case, we're looking at parts of the ocean. So wind is a measure of speed of the air flowing just over the surface of the ocean. Like we said, pH is a measure of how acidic or basic the water is. Temperature measures how hot or cold the water is, and salinity is a measure of how much salt's dissolved in a volume of water. Something else we're going to think about as we do this exploration is density. And so, density is basically how much mass is concentrated in a given volume. In this case, we're looking at water, so we're looking at water density, ocean water density. And when the temperature of water increases, its density decreases. So we would say they're inversely proportional. When one goes up, the other goes down. However, with salt, with salinity, when water salinity increases, the density of that volume also increases. There's just more stuff packed into the same amount of space. So less dense fluids will float and denser fluids will sink. So there's a little bit of a hint there of what's going on. So, if you have a part of the ocean where there's a lot of salt, it's heavy in salt, then it's going to be more dense. And we see here that dense fluids will sink, whereas maybe part of the water that's not as salty won't be as dense, and therefore it's probably going to rise above the saltier dense water. Page 1.4 is the next page, and this is where majority of the action is going to be happening. We're going to look at a virtual representation of all of the world's oceans. We're going to focus in on the Indian Ocean, and there's a little magnifying glass in the simulation. We'll sort of use that as a way to narrow in our focus, and then we'll use it again to explore data that's being recorded by these virtual NOAA weather buoys. And NOAA, by the way, stands for National Oceanic and Atmospheric Administration. So they're the ones that are basically in charge of kind of tracking weather patterns, climate changes, and also what's going on with the oceans. So they have a pretty big job. A lot of interesting folks there, scientists and engineers support and work for NOAA. So the data is on the next page. We'll see the data in sort of this table view, and then there's a graph view also. And then from the documents tools, which we'll see up here, we can erase that data. All right, so let's check this out. So this is I think this is a really pretty image of just the map of the world. And this red and blue ribbon that you see here is the representation of the oceanic conveyor belt. And so red represents warm surface water, and blue represents sort of a subsurface cool or cold water that's also flowing through the deep parts of the ocean. So there's the U.S. and South America, Africa, we have Europe, Asia. There's the other half of America over there, Australia, and so everybody's represented. And what we're going to do is to pull this over to the Indian Ocean. Well, there's the Atlantic. All right, here's the Pacific Ocean. Here's the Indian Ocean. So what it did is it gave us sort of a blown up picture of the Indian Ocean. And these little red triangular kinds of things, those are actually buoys that float in the ocean. And they're equipped with a bunch of different sensors to sense what's happening in this part of the oceanic world. So what I'm going to do is I'm just going to kind of go through these one at a time. We're going to collect some data, and so you'll get the idea. I'll go sort of slow on the first couple, and then I'll move a little more quickly because you'll basically have the idea. While I'm doing this, you'll probably also notice here in the video, you'll see this data table. It'll start to be filled in with information. So let me start here. We'll see this one's number 2, NOAA Weather Buoy number 2. The pH is 8.08, and so for reference, pure water, it has a pH of 7. It's said to be neutral. Things that are acidic are below 7, and things that are basic are above 7. So this part of the ocean has a slight basic pH to it. Salinity is 35.2, and this stands for parts per thousand. So if you get a volume of water and you count all the little particles and things that are in it. What this says is out of 1,000 things, 35 of those things are salt. Okay, those molecules are salt. Temperature 30 degrees Celsius, and the wind is blowing east southeast. Okay, that's what ESE stands for. All right, so weather buoy number 2, very good. We got that one done. Let's check this one out. Buoy number 3, pH is about the same, 8.07. Salinity is a little less, 34.4 parts per thousand. Temperature is 30 flat degrees C. Wind's blowing about the same, east southeast. I'm going to pick up the pace a little bit just so we can get through all of these. And we're capturing all of this data in that table. You are welcome to kind of observe and see what's going on. Hopefully I didn't skip one there. I think we're good. Looks like I missed number 1 to begin with, but it doesn't really matter. There's number 7. Number 8. pH bumped up a little tiny bit. Number 9. Yeah, pH is going up just a tad. Don't know if that means anything. There's 10, and I have to go back to 1. I have to get number 1 done, which I think is right here. Yep. All right, awesome. So that's our data collection. So this is sort of a virtual lab in a way. We're collecting data, and we're going to try to make sense of that data. On page 1.5 here, this is where we're capturing all of that data from the simulation. And so we have buoy, wind, pH, salinity, and temp. And all of the parameters are captured in the table. And then if you take a look, we have a graph. The graph's already generated based on the data. So and you can look at temp versus buoy. We can also look at We can also look at pH. Kind of groovy. Salinity and wind. And I think what we'll do is we'll start off with temp here, and we're going to go through some questions now on problem 2. And these questions are asking about information from the data set to try to understand what's happening with the simulation. So question 1 on page 1.6, set the y-axis to temp and the x-axis to buoy. What pattern do you notice? So we're going to go back to that previous page. And I'm going to try to overlay a picture of the buoys, so to give you some perspective. And so the buoys, you can see them they're all numbered. And the graph showing buoys 1 through 4, all about the same temp. Now, what you'll notice on the little picture here is that buoys 1 through 4 are close to the equator. They're closer to the equator than the rest of the buoys. And as we move away from the equator, see what happens to the temp. And then as we move back, toward the equator, temp starts to increase again. So, this is a nice pattern. It makes sense geographically. From that buoy picture, you can see as we move away from the equator and as we move toward the equator, the temperature of the water changes. Question 2, examine the oceanic conveyor belt shown on the main screen of page 1.3. When looking at the current located toward the west, closer to the coast of Africa, we can determine that this is a blank water current. So is it warm or cold? So going back to that, the image of the oceanic conveyor belt, we said looking toward the west, not the west coast of Africa, but actually the east coast of Africa, but just west of where we were. This is the coast that the question's asking about. And so if you look at that oceanic conveyor belt, you'll notice that the water, the current that's flowing up along that coast is blue, which indicates that it's cool or cold water. So question 2 would be cold. This is a cold water current. Okay, question 3. As you increase the temperature of water and you keep those other variables constant, what happens to the density of water? Well, we talked about this at the beginning of the lesson. If you remember, we said that as you increase temperature of the water, okay, the density of that water is going to go down. Okay, it's going to decrease. The molecules are a little more spread out, and so as a result of that, the water will be less dense. And conversely, as you decrease the temperature of water, in general, the density is going to increase. And so, these two things are inversely proportional to one another. They're inversely related, rather. Now, there's a special case when we get to freezing water, ice. But for this lesson, I think it's sufficient that you know that temperature increases cause density decreases. So it's going to be this one. Okay, question 4. Why would temperature have an effect on the current system? So basically, what is temperature doing to cause the motion of water, these currents? And if you think about the density differences based on the temperature differences, you'll start to realize that as the water cools down, its density will increase, and when the density increases, that volume of water is going to sink. It's going to drop in depth relative to the warmer, less dense water, which will be on the surface. And so there's this sort of constant motion of water being heated up, water being cooled down, that causes sort of this motion that we're seeing in the oceanic conveyor belt. Question 5. Upwelling is the process where cold, deep water returns to the surface and then becomes a shallow current. From examination of the ocean conveyor belt and buoy data, at which buoy is this process most likely to occur? And so we have 4 options: buoy 2, buoy 5, buoy 8, and buoy 10. Let's go take a look. Let's get back up here. Okay, and remember, up the coast of Africa, the east coast of Africa, the water's cold, and then it gets toward the Indian Ocean, and then it starts to warm up. It looks like there's probably some upwelling that's happening there, possibly. And so if we look back at those buoys, and I believe, if I'm not mistaken, I think buoy 2 was, let's get the magnifying glass here. Is this buoy 2? This was buoy 2. Okay, yeah. That's about the point where that blue turns to red and then comes back down again. So, here's Madagascar off the coast of Africa. And so you can see it there. And so I'd say just past that, at the very top of that circle of buoys was buoy 2. So I would say it'd be buoy 2 of the choices given. Okay, buoy 2. Okay, next question. Is there any observable pattern with the pH numbers from the different buoys? Well, let's go take a look. Let's go back up to the data and let's choose pH. Okay, so pH went from a range of 8.02 to 8.12. So there wasn't really any big change in pH from one buoy to the other. And I certainly don't see much of a pattern here, especially within such a narrow range. I mean, overall, what's interesting, and this doesn't relate to the question necessarily, but the ocean water is slightly basic. Neutral, pure water's pH of 7. Here we see that ocean water is, in the Indian Ocean anyway, is slightly basic. So it's anything that's basic is pH of 7, or pH of above 7, and anything acidic is below 7. In this case, it's everything's in the 8s, the low 8s. But no pattern that we can see. So that data for answering this particular question isn't all that helpful. But they collect that data for a number of reasons, not just for looking at the current patterns. Question 7, where is the cold water directly coming from before it gets close to the equator? And well, let's take a look. We have that nice image. All right, so the water's way down here, and some of it, one of the currents comes up near the coast of Africa. As it gets up toward the coast of Africa, it begins to warm back up. And this is an interesting pattern, because what you'll notice is the cold water it's close to Antarctica. It's super cold. And so that water's cold. It's near Antarctica. That cold water, some of it comes up through this current off the coast of Africa, Madagascar, and then gets up into the Indian Ocean, and it turns warm. So that answer would be the south near Antarctica, which would be this one. Question 8, does the wind pattern match the overall flow of the current? Well, not really. We said that surface currents typically are wind driven. That's not always the case, but a lot of times it is. But in this case, it's a little different because what we have is sort of this cold water current, some upwelling that's happening in certain parts. You'll notice, like on this side, as that warm current goes up and it gets close toward the poles, it cools off, and then it comes back down, and it comes all the way down here, comes back up again, and then switches over again off the coast of California. So it's pretty interesting. It's not necessarily related to wind direction, though. So we're going to say, or wind pattern rather, so we'll say no. Question 9, what type of current is guided by wind? And we already know that. It's the surface current. So these are the ones that we feel when we're in the water. Question 10, deep ocean currents flowing into the Indian Ocean are very salty. When these currents upwell to the surface, that means they rise to the surface. Which of the following would likely increase in the region of water around the upwelling? Well, let's you know what, we can kind of take a look at some of this. If we go up to this image here, and if you recall, buoy 2 is kind of where the switch over from cold to warm happened, the temperature difference. And then those buoys kind of circled around this way. So we had buoy 1, 2, 3, 4, 5, 6, 7, 6, 7, 8, and 9 were all down here. And so it's interesting that toward the Indian Ocean that water is very salty. Well, let's take a look at the graph. Let's look at salinity. And the water with the most concentration of salt, dissolved salt in it, is buoys 1 and buoy 2, buoys 9 and 10, but the least amount are 7 and 8, which were the lowest buoys. So it's not a completely obvious pattern here, but there's some interesting data. The closer you get to the Indian Ocean, the saltier the water is. Well, we can see some evidence of that with buoys 1 and 2. And the farther away you get from the Indian Ocean, looks like it's a little bit less salt. The range here isn't huge, 33 to 35.4, and these are parts per thousand. So that means that there are 35.4 of all the stuff that's in that concentration of water. Out of 1,000 things, 35.4 are salt molecules. So that's kind of what that means. So I think we could safely say that which of the following would likely increase in the region of water around the upwelling. So salinity is going to increase, which I need to fix that. All right, question 11. The water in an Arctic region is very dense, causing it to sink down towards the ocean floor. This process is called downwelling. So we saw upwelling means that the water is rising. There's a density difference. Which of the following best describes water that's downwelling? So the options are warm fresh water, warm salty water, cold fresh water, and cold salty water. Well, we're talking about the ocean. We're going to talk about things that are going to increase the density, which is going to cause downwelling to happen. So warm water, that's out. That's not an option. It has to be cold. So these first two are gone as options. So we have these two that are left. So of these two, which one would be more dense? Would it be cold fresh water, or would it be cold salty water? Well, of course the answer is cold salty water. So we said as temperature decreases, its density will increase, and also salt dissolved in water causes its density to also increase. So it's choice D there. Okay, question 12. Which factors have an effect on upwelling and downwelling in ocean currents? And it says select all that apply. Whenever you see this sort of select all that apply, it implies there may be more than one correct answer. Okay, so it's not asking which one causes upwelling and downwelling necessarily. It's saying which factors have an effect on upwelling and downwelling. So what variables contribute to one or either, or one or the other, or in this case either. So we know pH didn't seem to have much of an effect. We know temperature, that's a definite. We said wind didn't really have anything to do with those deep ocean currents, but temperature seems to, and salinity seems to, so these are the correct answers. Question 13. The current system is driven by a process known as thermohaline circulation. And so basically the word haline or haline means salt. Okay, and thermo obviously means temperature. So we're talking about temperature salt or thermohaline circulation. The presence of changing temperatures and changing densities of salt within the water cause sort of this upwelling and downwelling process, which is helping to drive those currents, those deep ocean currents, the oceanic conveyor belt. So that's kind of cool. That's really what's going on there. And so that's why there's deep ocean currents. It's not really driven by wind. It's really primarily driven by temp differences and salt density differences. Okay. All right, well that's the end of this lesson. I hope you enjoyed that. Next time you're at the beach and you're playing around in the water, you can tell your friends or the people you're with about the oceanic conveyor belt, which is pretty cool stuff. It's really interesting to learn these kinds of things and to understand how our planet works. And I'm glad you were able to share some time with me, and I look forward to showing you some more videos here in the near future. So please check back on our YouTube channel. It's TI Calculators, all one word. Also, make sure you take a look at TI-Nspire.com, where you can find this activity and many, many more. And to use the TI-Nspire CX Premium software, all you have to do is go to our website at education.ti.com. Have a great day. Thanks very much.